He used to be here. We all remember him. Did an amazing PhD with Ramesh. And then went to Princeton. Our competitor, we should ask him, is the experience as good as here? But I guess you don't need to answer that. And we'll hear from Andrew about why are electrons in hot black hole accretion flows so cold. And after that, we'll hear from Aaron Meisner, who shares an appointment with NOIRLab, the ITC Radcliffe Institute for Advanced Study, and he will talk about the coldest solar neighborhood subdwarfs. And then we'll hear from Kragh Jespersen from Princeton again. So we have two Princeton visitors today. And he will tell us about the optical and infrared are connected. Can you just explain in which context?
Galaxies.
Galaxies, okay. And then Swati Ravi from MIT will tell us about probing variability in X-ray polarization with Bayesian nested sampling. Andrew, take it away.
Yeah, thank you so much for having me. So last time I was here was right after I finished my PhD, and we had just come up with the first EHT image of M87. And we've been quite busy since then as part of the EHT collaboration, imaging M87 several times since then, as well as Sag-Star. And in particular, starting to look at their polarization, which is telling us a lot about the magnetic fields around these supermassive black holes. And the polarization here, you can see, is indicated by these nice swoops in both sources. So both of these sources, look very similar. They have ring-like emission at sort of at 230 gigahertz on event horizon scales. They're both incredibly well described by these GRMHD simulations, which we run of hot plasma around supermassive black holes, despite the huge thousands, the 3 magnitude difference in the black hole mass in both cases. Both images have taught us a lot about the accreting plasma magnetic fields and the mass and spin of both sources. So in particular for M87, we know that it's the emission region that we're observing around it is hot. It's this hot accretion flow of temperatures exceeding 10 to the 10 Kelvin, geometrically thick, very sub-Eddington emitting synchrotron radiation. We think by looking at the polarization images that it's magnetically arrested with these strong ordered magnetic fields that thread the event horizon. And that sort of gives us a very nice understanding of how it could launch this powerful relativistic jet by the Blanford-Zernike process of these strong ordered magnetic fields extracting the spin energy of the black hole. So like I said, we interpret these images using these GRMHD simulations, general relativistic magnetohydrodynamic simulations of plasma going around the black hole. But these simulations have a problem in that these hot accretion flows, like we're observing in M87 and Sag-Star, are intrinsically too temperature. They're so dilute and so hot that the electrons and ions can't collide, and they're not in equilibrium with each other. However, the GRMHD simulations are assuming that the system is described by a fluid, and they only solve for a single combined fluid temperature. And then so as a result, in order to get images from these simulations, like this beautiful movie here on the right, which we can then compare to EHT observations, we have to sort of set this electron temperature on top of the simulation somehow by hand, which we typically do in post-processing using this family of parameterized functions. In particular, the sort of classic family that we've alighted on for the EHT is this R-beta model developed by Monika Moskiroska, which tells us that the ion-to-electron temperature ratio, which we sort of paint on top of the simulations, is a function of the plasma beta, or the ratio of the gas to magnetic pressure. And in particular, it transitions from a value which you can set called R high at high plasma beta to a value called R low at low plasma beta. And this is just sort of something which is developed based on intuition from small-scale simulations of plasma heating, but is something that we just sort of apply wildly with all sorts of values of R high and R low to these simulations to try to get images which look as close as possible to observations. And one thing we found, which has been a little confusing, and I would argue is very surprising, is that when we compare the polarization images from the EHT to our library of simulations, we actually are starting to prefer values of this R high parameter, or this ion to electron temperature ratio in the high beta case that are very high. And so like in excess of 100, potentially a difference between the ion and electron temperatures. These models with the low electron temperature compared to the ions, or large R high, are more compatible with the data because they produce much lower fractional polarizations that are consistent with what we observe in M87. So here, this band is what we have observed in M87, and these distributions are different simulations with different R high values. And the reason this is because all this depolarization, the only way to get the level of polarization which we observe in M87 is through Faraday derotation. So synchrotron radiation like we observe is intrinsically very high polarization, but when we have a bunch of Faraday rotation rotating the direction of the polarization vector as it travels through this hot plasma, if that's happening at sufficiently small enough scales so that it tangles up the polarization at infinite resolution, when we blur it to the resolution that we actually observe with the EHT, we can get this low polarization fraction by sort of canceling over this scrambled polarization pattern at the infinite resolution scale. So you need sufficient Faraday rotation to do this scrambling, but the Faraday rotation is really sensitive to the temperature of the electrons, and in particular, it really wants the electrons to be colder in order to get sufficient Faraday derotation. So that's why we have arrived at that. So as a PhD student, and then now recently again, I have started up doing this campaign of 2 temperature simulations, which instead of taking the simulations and then assigning an electron temperature after the fact, these 2 temperature simulations include radiation feedback and they include different subgrid plasma heating models, and they try to answer more self-consistently what the actual electron temperature you would predict is based on some physical models for the processes that are heating and cooling electrons. And these simulations are an order of magnitude more expensive than the traditional GRMHT simulations. They're much harder to run at scale, but last year I ran the first sort of survey of many different black hole spins, looking at a single electron heating model based on Landau-Damp turbulence, which is happening at the subgrid scales to actually put heat into the electrons. And this is what they look like sort of in snapshot, and here's what they look like in their polarization blurred. And so sort of the key takeaway is that these simulations, they look a lot like the standard GRMHT simulations in almost all of their bulk characteristics, things like the overall magnetization on the black hole, the jet efficiency that they produce, the spin down factor that they produce. Even the average polarization pitch angle as a function of spin is sort of following the same trend which we observe in standard GRMHT simulations, but they predict an electron temperature which is far too high to produce the overall level of depolarization which we observe. So they basically predict way too much polarization on the order of 20%. And with the EHT in 2017, we were observing something closer to 7 or 8%. And with even these new observations which just came out last week, we're preferring things that are even lower than that, maybe like 3 or 4%. So this sort of best model we have for realistic subgrid plasma heating that is taking the heat that is produced from material falling into the black hole and partitioning it between electrons and ions is producing a system which is way too polarized to explain observations. And I think this poses a real challenge to sort of our understanding of what is actually heating electrons in this region. So the first immediate thing you might ask is, what about different plasma heating mechanisms? I haven't run a full survey of simulations with sort of one of the alternative models, but I have one when I was a grad student that was based on heating from magnetic reconnection. This sort of gives you a different answer for how energy is partitioned into ions and electrons. And you can see it produces somewhat cooler ions relative to electrons, sort of an effective R high parameter of 14. This is the effective sort of ion to electron temperature ratio at high beta. But even that is not enough to produce sufficiently depolarized images. We really are preferring from the EHT things like closer to 50 or higher. So I think this is a real challenge to sort of our understanding of what's going on in M87. I think explanations for what's going on is that potentially turbulence is more important than we actually think in these simulations. Maybe we're underproducing turbulence, or M87 isn't actually magnetically arrested, though there's lots of other evidence that points in that direction. Maybe our models underpredict the accretion rate or the importance of radiative cooling, but on the other hand, the models do a very good job of explaining the overall image structure and total intensity, and there's a lot of other things that would change if you just started dialing up the accretion rate. I think the most likely situation is that we just aren't treating these plasma heating models correctly, and there's either too simple or missing sort of a key heating channel that would explain how electrons are heated, but not as much as the current sort of best models we're blindly applying predict. So I don't know the answer to this, but I think the main takeaway I would leave here is that, when I was a grad student, I was trying to say that we could test plasma physics theories with these black hole images. We could actually use these images to learn about how electrons and ions are energized or near close to the event horizon. I think at the time that seemed a little far off in the future, but I would say the time is actually now. We now have the data we need to probe plasma physics at the event horizon scale. We sort of have a contradiction between these images and our best theories of how plasma is heated in these regions. And yeah, I think there's a lot we could do to hopefully resolve this tension. So happy to hear any ideas if you have them. But yeah, thank you.
Thank you, Andrew. You started in the first slide with an estimated temperature of about half an MeV. And that's pretty close to the electron rest mass. And so the question is, could collisions in these plasmas, they could be proton-proton, they could be electron-proton, generate pairs, and that would change the entire balance that you're considering. And do we have any constraint on pair production?
Yeah, no, that's a very good question. So almost all the GRMHD modeling completely ignores pairs and just assumes an electron-ion plasma. And I totally agree, there are many different channels that could produce pairs in these systems. And we think that jets, much of the jet plasma we observe at large scales is pair dominated. And so exactly how pairs are produced, how they, what fraction of the emission they make up is, I think, a really good question, and one that we are sort of completely ignoring in this work. I would say we know that the plasma that we're observing can't be entirely pairs, and that's because pairs would have no parity rotation, right? And we need this parity rotation, because we think we need this parity rotation to produce the depolarization which we observe. So I would actually think that if you started adding pairs, you would make the problem harder in some sense, but I haven't done the detailed modeling on that one.
The question is, what does nature do, not what we find out there?
That is true.
Ramesh and then Charles.
So Andrew, you posed the problem as saying that you can run a simulation with all the physics, you get much hotter electrons. EHD models demand a much cooler population of electrons. Now, leaving aside the models, the observations directly give us a brightness temperature, right? And those temperatures are low. They're typically like 10 to the 10K, few 10 to the 10K. But they are beam smeared. So I'm just wondering, do the observations themselves already pose a conflict with your newer simulations?
Yeah, I mean, I would say the conflict that they pose is primarily this higher level of polarization.
No, leaving aside, I'm just talking at the level of intensity and surface brightness.
At the level of surface brightness, I don't think so, no. I think you can look here, I think the image shape, the sort of morphology at 230 is, in total intensity, I think is relatively consistent. But I do take your point, like an explanation could be that sort of the overall plasma temperature is lower, and that we're producing just too hot ions in the GRMHD simulation more broadly, and so therefore we need to sort of apply a penalty to them to get the electrons to be lower. Yeah.
We have another question from, by the way, the microphone for some reason is not working now. It's used to it. I'm not sure. Anyway, Charles, go ahead.
Okay, Andrew, so before I ask my question, I want to state that I'm a loyal fan of the EHD. But should we take the reported measured polarization this seriously? Could it just be an error in the analysis?
No, I don't think so. I think we're very careful in how we approach measuring these quantities, and I think we always run our measurements through many different simulations or different reconstruction pipelines, and try to sort of really only report the measurements which are consistent among all the different possible choices that you have to make in converting the raw data to a polarized image. And yeah, I would say that the results we're comparing against here are sort of the most conservative results we could arrive at from the EHD. Like, if you take a individual reconstruction from a single method, for example, or a single, you don't really see this band here, I guess, on the screen, but there's a band here representing EHD measurements. I think individual modeling pipelines will give you a much tighter range, actually. And so we're sort of comparing the broadest possible, to the most conservative results we can possibly get from the EHD.
But of course, the models are reflecting our imagination, and nature may have something else, so we may not explore all possibilities.
Yeah, no, I completely agree. On the modeling side, we may be just completely off. It's possible. I think the GRMHD paradigm does a very good job in many respects, and so I wouldn't throw it out right yet, but there could be things that we're just ignoring there. But I think on the data side, on what the actual measurements we're comparing the models to, I have pretty high confidence in those.
Any other? Yeah, Elise.
You mentioned that you might have not accounted for enough turbulence to reduce the polarization. Do you mean only turbulence locally to the source or along the line of sight?
Yeah, I was mostly thinking about turbulence locally in the source in the accretion flow, but it is possible, yeah, if you somehow had some extremely turbulent region in between you and the black hole, maybe that could provide enough sort of small scale Faraday rotation. I have to think about the actual numbers there, but I think that's interesting.
Well, we definitely know that the interstellar medium is, because of the extinction, there is a lot of material,
Yeah.
but the question is, what angular scale are you talking about here? It's milliarc seconds. So the
Microseconds, yeah. I think you would need different patches of Faraday rotation on sort of the, sub 5 microarc second scale.
micro seconds, so very small scale,
yeah.
but it's not.
Absolutely.
Yeah, it's possible because there are structures on the scale of 10 AU in the interstellar mediums.
Yeah.
Yeah. Any other comments? Let's thank Andrew again.
That's the first time I've heard a temperature of 10 to 10 degrees be referred to as low.
Okay, no worries.
Just speak louder.
Yeah, so my name is Aaron Meisner. I'm an astronomer at NOIRLab. I'm ordinarily based in Arizona. This year I'm on sabbatical as a Radcliffe Fellow here at Harvard, and so I'm grateful to ITC for giving me this joint visitor status for the upcoming academic year, and also for giving me the chance to speak briefly today. I'll also say that several years ago, I was a PhD student here, though in the physics department, and I was advised by Doug Finkbeiner, who's also involved with the ITC, so it's great to be back. As an initial matter of terminology, before I jump into the rest of the talk, in the context of low mass stars and brown dwarfs that I'll be speaking on today, a subdwarf means low metallicity or metal poor objects. So the topic today is old and cold brown dwarfs. Before we get to old and cold brown dwarfs, I just want to motivate a little bit why we might want to study cold brown dwarfs in general, and I won't read all of these, but a few I wanted to highlight is that they make for great exoplanet atmosphere analogs because they overlap in mass and temperature with giant planets, but you don't have the glare of a host star, making it easy with, say, JWST to really see a lot of molecular absorption in their atmospheres. The initial mass function, that's also quite interesting, going from the lowest mass red dwarf stars all the way down to Jupiter masses. Does the mass function have a cutoff or not? And if so, where? And also, I'll show an example of this later in the talk, but there's connections to planetary science. We can better understand and contextualize our own solar system's giant planets by studying a diverse array of whole brown dwarfs. And for the three cases I highlighted here, I would argue that the very coldest brown dwarfs are perhaps the most crucial, just in terms of temperature, say they're the most Jupiter-like, for example. So about 15 years ago, there was a NASA mission called WISE, Wide Field Infrared Survey Explorer, which really revolutionized our view of the infrared universe over the entire sky, and it also really changed our picture of the very local solar neighborhood in our Milky Way. So there are well-known systems like Barnard's Star and Proxima Centauri that are our closest neighbors. They've been known for over 100 years. But then only within the past decade or so, this plot got further populated with some very cold brown dwarfs that turn out to be now the third and fourth closest known systems to the sun. And in particular, I wanted to highlight WISE 0855, shown there with the white arrow. It's a 250 Kelvin, or maybe a little warmer brown dwarf, and it's only 2 parsecs away from us. And so this led us in the brown dwarf research community to think that, well, if we just dig deeper and push further out in the solar neighborhood, we should be able to find a lot of very cold objects, similarly cold to WISE 0855, or maybe even colder, approaching the temperature of Jupiter, which is more like 150 Kelvin. So we spent many years doing this, digging deeper in the WISE data to, as we thought, try to find the coldest brown dwarfs potentially approaching Jupiter's temperature. And there were many avenues that we went down to try to do this. One is this effort that I led for many years called Unwise, where we took all of the WISE data, we downloaded every exposure they had ever acquired, about half a petabyte worth of imaging, and we processed the entire sky worth of data to make the deepest and cleanest possible maps and catalogs. So you're seeing an example here of just the fact that naturally by co-adding, you can go deeper than an individual exposure, and you can also suffer very little loss of information for proper motion objects in the solar system because they don't move as fast as asteroids. And so you're essentially getting the best of both worlds by going deep and still preserving proper motion objects as point sources. Another avenue that we pursued here in combination was this project I launched called Backyard Worlds. And the idea is that this is a universe project where we put many dozens of terabytes of WISE data, unwise data on the internet and let tens of thousands of people join with us in the quest to find these cold brown dwarfs. And the reason we thought this would be an appropriate thing to do is because when we're trying to find the coldest brown dwarfs, we're looking for high proper motion as a proxy for their nearness. And the human eye brain is very good at the pattern recognition task of trying to find objects that move across the sky, and this is similar to how like Pluto is discovered with the comparator.
Better than AI?
That's an interesting question that I'm interested in exploring. We've also been using like neural networks applied to the pixel level data. The thing is that any search you run algorithmically, even with AI, there's just so many artifacts and so much noise that when you're looking for like a small handful of objects out of many billions of stars and galaxies, you get overwhelmed by the false positives. So at some level, we really value the human review at the end before we would follow up with something like JWST or Keck. But long story short, we actually haven't discovered any of these cold brown dwarfs as cold as WISE 0855 or colder. We haven't discovered any Jupiter temperature brown dwarfs, which has been surprising and frustrating to us actually. So the question then is, why haven't we discovered any Jupiter temperature brown dwarfs yet? And so in the last few slides, I want to show one extreme example of the following 2 points or hypotheses. So perhaps the coldest brown dwarfs are very diverse, like the giant exoplanets and the giant planets in our own solar system, right? So Jupiter and Saturn, they don't look the same, despite being members of the same solar system. And then the other thing you might think is that maybe we need to understand the oldest brown dwarfs in order to properly know how to search for the coldest brown dwarfs. And the reason that this intuition is plausible is because at a fixed brown dwarf mass, the oldest brown dwarfs will preferentially be the coldest because they've had the longest time to cool over many billions of years. So I'm going to show one really remarkable example of a cold and old brown dwarf that we found called WISE 1534-1043. It was nicknamed the accident by the citizen scientist who discovered it, so that's how I'll refer to it. The unwise image blinks in which we originally discovered it are shown here. And you might actually be reasonable to think that, well, we just stared too hard at the noise, this doesn't even look like a real object. The reason it's off-center is because we thought we were looking at a candidate in the center and happened to accidentally notice it moving in the corner. This is a very unusual outlier object, so these two color magnitude and color diagrams are sort of the standard sequences of brown dwarfs, and they follow a pretty uniform pattern in terms of the 20 parsec LTY census. But then this object, the accident, is either a 6 or 8 magnitude outlier, depending on which plot you look at. So it's kind of in a quadrant all by itself relative to the rest of the population of LT and Y dwarfs within 20 parsecs. Again, you might think this all just means we were looking at noise in the image, but we did eventually get Spitzer follow-up and detected it, as well as Hubble follow-up and detected it. So this is what we knew about the object pre-JWST. We were able to get JWST follow-up, which I'll show in the next couple of slides. So what we now know is that because this object has a total proper motion of 2.7 arc seconds per year, which is quite high. Barnard's star, for example, the highest known is like 10.5 arc seconds per year. When you combine that with its parallax, which puts it at 16 parsecs, that's a tangential velocity of greater than 200 kilometers per second, which even without a radial velocity means it must be in the halo. And additionally, just from the absolute magnitude relations as a function of color just from the absolute magnitude relations with respect to temperature, we also know that it's about 500 Kelvin once you have the parallax and the luminosity. So in cycle 2, I was able to submit a proposal that got approved for a JWST follow-up of this object. And we were expecting the spectrum to be weird, and it turned out to be maybe even more surprising than we had thought. So this is the spectrum from about 1 to 5 microns. And what we find is that the accident spectrum is unlike that of any other known star or brown dwarf. In particular, the only molecules that you can see absorption from here are methane, water, and silane, whereas in most brown dwarfs, this called the Y dwarfs, you would typically expect the spectrum to be strongly shaped by carbon monoxide and carbon dioxide absorption, but those are totally absent in this spectrum. And the silane detection is also very unexpected and novel. For decades, it had been thought that silane should be somewhere in Jupiter and Saturn, but it had never been able to detect silane, even in our own solar system, nor in any other brown dwarf or any exoplanet. And so this, again, is a really nice example of the connection between the coldest brown dwarfs and planetary science and exoplanet science. We also get a metallicity that's extremely low of less than -2 dex, and we confirm the very low temperature. So, it's kind of weird, like, why is there an object at this cold and this low metallicity so close by to us? So just to hammer on the points about the diversity, potentially, of the coldest brown dwarf, similar to how giant planets are diverse, this is a temperature sequence of the coldest known brown dwarfs that we've been able to get JWST spectroscopy for. At the top, you have warmer objects starting at about 800 Kelvin. At the bottom, you have the coldest brown dwarf at about a little less than 300 Kelvin. And so when you put the accident into this temperature sequence, it really just is not in the sequence at all, no matter where you put it on this plot. So this is a good example, I think, of clearly we're not going to get a nice one-dimensional temperature sequence of the coldest brown dwarfs. They're much more diverse than that, and we at least need a second dimension of metallicity if we want to understand the range of spectra that's seen for these old and cold objects. So with that, I'll just conclude about some ongoing and future directions. We need more than just this one object to try to understand the sequence of the coldest brown dwarfs, including as a function of metallicity. So we're trying to map the 2D spectral sequence of brown dwarfs in terms of both temperature and metallicity. Good time. I'm very interested in sphere-X spectrophotometry because having processed all of the WISE images for many years, it just seems like a great opportunity to really dig into an interesting image-based data set. So if folks here are experts on that, I'd be really interested to talk. I'm also interested to learn more about the deep searches into the thick disk and halo, further from the solar neighborhood with, say, JWST or Euclid, etc. I'm also interested in the topic of trying to use JWST radial velocities to complete the kinematics for old and cold brown dwarfs, and then potentially associate them with specific substructures within the galactic halo. So thank you.
So the fact that you detect a halo dwarf within 16 parsecs, that's amazing. It means there is a very high number density of such things, just by chance. And we have a limit on how many halo objects, compact halo objects, should be there for microlensing. And so I wonder if the limit from the Macho experiment, I mean, it was on white dwarfs and also these dwarfs. So did you look into that to see if it's compatible with the fact that you detect one so close to us?
Yeah, I can't remember exactly with regards to the Macho limit specifically, but I have thought about, what if the mass function is really tilted towards very low mass cold objects at low metallicities. But it's just, even if you had a big factor of several increase in the mass function down there of the brown dwarfs, it's still not enough to be an actual dark matter.
No, not dark matter, but yeah. The question is the number density of such objects. You want them to be abundant enough to see one, the nearest one, within 16 parsecs. That's roughly the mean distance, let's say, between them. And that gives a very high number density because it's competitive with the local population, right? So the halo is usually much more rarefied than the disk. And so the fact that you see such a high density means that it should have showed up in the Macho experiment because these would microlens, the LMC. So it would be interesting to check if it's consistent.
Yeah, I vaguely recall that we have looked and it wasn't a problem, but yeah, it would be good to recheck that quantitatively for sure.
Dave?
Yeah, so for the accident, where's the carbon and why are you seeing silane? Why is the spectrum so different?
I think the basic idea is that in such a low metallicity environment, something like CO is two metals, and so it's just harder to do that, or CO2 is two metals, harder to do that, and so the natural thing for the silicon to do something with is the hydrogen in this very low metallicity object. And there is some carbon and methane that we see there.
Because, one of the surprises, of course, is that we see a lot of CO and CO2 in objects that are much colder than we expect, and that's associated with dredging and convection. But I wonder in such an ancient object if that convection has now become very suppressed. We're just seeing less of that uplift of hot material.
Yeah, to get the silane to be observable in the spectrum, we had to invoke strong vertical mixing.
Oh, so it's the opposite?
Yeah.
Okay, interesting.
And we also did look at fitting the C to O ratio, and that was consistent with other halo stars. So that sort of fit into this picture that this is an object formed like a star, but just with much lower mass and had a very low metallicity.
Yeah. Great, thank you.
Usually low metallicity implies high mass stars, but you're saying they make also small low mass stars. That's also a puzzle.
Right. It's an open question as to whether low metallicity would tilt the mass function such that you have more objects at the low end or fewer objects at the low end. So
theoretically, it's fewer.
Okay. Yeah. Observationally, one thing that we need in addition to the spectral sequence is we need more parallaxes to get luminosity so that we could actually do real space densities of these things. So it's a little early for all of that, but yeah, the mass function is a very interesting part of this, I think.
Any other questions, comments? The accident is very interesting. Let's find more, and maybe the Rubin Observatory will help you.
Yeah. So at NOIRLab, I have worked on Rubin Observatory for many years. Rubin will be great for pushing further out into the thick disk and halo, right? Because it's natural to think that if you want to preferentially detect lower metallicity objects, you should just move further out in the solar neighborhood. Like you shouldn't be looking 10 parsecs away. You should just look hundreds of parsecs away. One limitation with Rubin, though, is that it won't be great for the very coldest, like 500 Kelvin. But there's an intermediate kind of T-dwarf 1,000 Kelvin temperature range where it'll be very interesting for low metallicity objects there.
Thank you.
Good. All right, I'll get the microphone since it seems to not be working. So please, anybody, if you can't hear me, let me know. So my name is Jespersen, and I'm a final year graduate student from Princeton, where I broadly work on all things galaxies and astrophysics related under the supervision of David Spergel and Peter Melchior. So when you, like me, need to propose writing a thesis on galaxies, one of the first questions you have to answer is, what kind of data am I going to use? When I had my first thesis meeting, the thing I proposed was to use optical spectra. After all, optical spectra is something we have in abundance, and it's a very information-rich data type. Of course, that meant that somebody on my committee then immediately objected, saying, well, that's a decent idea, but there's just so much that you'll never know about galaxies unless you have access to information from the infrared. Somebody then objected to the first objection, saying, no, actually, I think that everything you need to know is in the optical spectrum, so we really should need this. And that meant that my thesis meeting, which was of course supposed to be a meeting about my thesis, very quickly evolved into a meeting about the question, how much can I tell about the infrared emission of a galaxy, given that I only have access to the optical? After a little bit of debating back and forth, it became a much more well-defined question, can I predict the mid-infrared photometry of a given galaxy from the optical spectrum down to the noise level in that photometry? And so the question that split my thesis committee in two, with one side saying that it, of course, was completely obvious that you would not be able to do this, because after all, when you have an optical spectrum, the thing that you're really probing is stuff like stars and gas emission lines. I mean, in the IR, you're just seeing distinct components like PAHs or hot dust heated by AGN. While the other half of my thesis committee was arguing that while that is definitely true, those things are so strongly coupled to each other physically that you should be able to make the bridge from one domain to the other. So this debate really came down to this, the assumptions that you make about the coupling strength between different components in galaxies. Of course, we need a way to figure out who's right, and for that we need some data, because as Robert Lupton at Princeton would say, data always beat assumptions. And the data we're going to be using is 500,000 SDSS spectra cross-matched to Y photometry, which Aaron introduced before, at 3.4, 4.6, 12, and 22 microns. And then we're just going to make an empirical mapping to go from the optical to the IR photometry. Exactly how we make this empirical mapping doesn't really matter. All that you really need to know is that we, of course, fit our empirical mapping on one subset of our data and then test it on another subset of our data. So just as a reminder, if I can actually predict the mid-infrared photometry starting from the optical spectrum, then my residuals will fall on these nice unit Gaussians, and if I can't, it will be much more broad. So let's see what I get. And this is what you get for your predictions. So the mid-infrared photometry of galaxies is definitely predictable from the optical spectrum, which implies, again, in turn, that the underlying physical components of galaxies are very, very tightly coupled physically. Now, of course, we want to think a little bit about why the very smart and intelligent and distinguished scientists on my committee thought that this wouldn't be possible. And at least one of the culprits is the way that we as a community tend to construct galaxy SED fitting codes. If you ever read a paper on how to fit galaxy SEDs, you're very likely to come across a plot that looks something like this, which varies one component completely independently from everything else in the galaxy. Right? This would imply that actually I wouldn't be able to predict anything going on in the infrared from the optical because this parameter, these AGM parameters here just vary up and down completely freely. But we know that this is not the case. However, this is the way that we always construct codes to infer the properties of galaxies. So this begs the question, what would happen if I make these codes do the same task? Fit in the optical and predict in the infrared. So we tried to test two of the premier codes in the world right now, one called Chael and one called Prospector. Here I show the residual plots for Chael in green and Prospector in blue. And now you see that they really don't know how to make these predictions. This shouldn't be that surprising, again, given that you have this assumption of separability. What is more surprising and more statistically worrying is that they're very, very confident in their wrong predictions. If we just take a sample galaxy and look at and take 100 draws from the posterior of Prospector, you'll see that not only is the central value off in the data in red, it's an extremely confident wrong answer. What's really happening here is because Prospector is a very, very good model. It's one of the best we have. It's still far from perfect. And every time you take an imperfect model and use it to fit data, that imperfect model will use any and all three parameters it has, no matter if it's physical or not, to try to cover up its imperfections. This often leads to phantom measurements like detections of giant AGNs that just don't exist. AGNs are interesting because AGNs are one of the few things that you could really argue for being physically distinct from the rest of the galaxy. After all, a nice black hole image shows us that black holes are much, much smaller than the galaxies they reside in, so they have very different evolutionary timescales. And they're often also shrouded by a dust torus that blocks out most of the optical light around it. But we know that when we do predictions using our empirical model on the AGNs, we still get the photometry right. Of course, when you're at Princeton and you have anything to say about AGNs, you have to go and consult with the two local experts, Jenny Green and Andy Goulding, and they'll tell you that, like, yeah, it's cute that you can predict the photometry, but we don't really care. We want you to predict something physical about the black holes. If you can predict the volumetric luminosity of each AGN to less than 0.3 dex accuracy, we would be amazed. So of course, we can go and do an X-ray selection out of our SDSS sample and then do this test and see how our residuals fall. And it turns out that when we do this, we get a typical error of 0.33 dex. So we don't quite beat the mark that Andy set out for us, but we do well enough to earn us a very, very rare, that's quite impressive, from Andy. Of course, when you're using a code like Prospector to fit the optical, you're not usually looking to fit AGN parameters. You're looking to fit stuff like stellar masses and star formation rates. The problem with just saying I don't actually care about AGNs, I just want to fit my star formation rates, is that these two parameters are extremely degenerate with each other. So if you make a big error in your AGN luminosity, you'll make a correspondingly large order of magnitude error in your star formation rates. So you cannot get out of caring about the AGN. Of course, this, all of this isn't so much to criticize the current models as to actually provide a roadmap for how to improve the next generation of galaxy models. One of the ways we can do that is by making maps over what information we're exploiting that Prospector is leaving on the table. And when we do that and we look across the entire spectrum, we get maps that look something like this. One of the main things that you'll of course see is something somewhat unsurprising. If you could just get H alpha wrong in these, if you could get H alpha right in these models, you would make a pretty substantial improvement. So while this is the biggest single feature that you need to improve on, there's also a lot of substructure in this plot here. And most of these little wiggles here, they're not noise. They are very easy to identify with metal lines. And that's because these different metal absorption lines from metals like iron, strontium, and barium together can provide you with an extremely detailed plot of the formation history of each galaxy. So these are some things that will be very, very interesting to see in the next generation of SED codes. So just to summarize, optical and IR are very tightly coupled. They can only be that coupled if the underlying physical components that dominate the optical and IR are also very tightly coupled. All SED codes in the world today do not respect this fact, all bridges, and combining that with the slight model specification we have in these models leads to bias and imprecision in the inference we get. Luckily, data models can help fix it, and if you want to know more, you can either go look at this very nice paper detailing all of it, or you can come find me in the D412 throughout Tuesday. Thank you.
Yes, it's also interesting that the infrared background and the optical background are comparable magnitude, and it didn't need to be that way unless, yeah.
It didn't need to be that way, but if there's one thing you learn from doing astrophysics, it is that everything is connected with everything, is connected with everything.
Yeah. But the assumption is that infrared is coming from dust, but you are saying no, it could be intrinsically somehow correlated.
Intrinsically correlated, yeah, that's my argument. I think it's the thing that the data show.
There was a question, yeah, please.
So, thanks for the great talk. I was wondering what you thought about, so you mentioned that it's mainly from broadline AGN that you were making the comparison for the luminosities. What about for narrowline AGN?
So we do actually have narrowline AGNs in here. So the blue thing here, so we're doing an X-ray selection for the AGN. So we're selecting across broadline and narrowline and things that we don't even really detect very clearly in the optical. Clearly, our predictability going from the optical spectra are better when there are broadlines in the spectrum. Like when there are visible broadlines in the spectrum, it's much easier to make a prediction, but we still do a pretty good job even when we don't see anything.
Have you looked
at sorry.
One quick follow-up. Have you at all just like explored with, like, for example, like a line, like a ionization feature like neon 5 correlated with like a AGN luminosity or anything? That might be an interesting understanding.
I agree.
Go ahead.
Now, do you have something to say about the BPT diagram that supposedly separates AGN from star-forming galaxies?
Well, yeah, I do think actually it's pretty effective. But what you're seeing here, right? If you're training an empirical model that can make essentially a very high-dimensional version of the BPT diagram, where I wouldn't be surprised to find a much cleaner separation than a normal BPT diagram.
Any other questions, comments? Yes, go ahead, Tony.
To what extent does this hold up for galaxies at very high redshift?
So of course we only go up to a redshift of 1, but we try testing it just to see, like, does this actually provide a good description? And we can't do. Of course we're fitting this on Ys, so we have to change it a little bit so that instead of predicting absolute magnitudes, because there the empirical model is kind of bounded, we're predicting colors. But that works pretty well for high redshift galaxies as well, up to a certain extent. We don't have a lot of optical spectra up to redshift 10. But we have tried this out on the weirdest galaxies we could find, like up 220, Markarian 231, and it still works pretty well.
It's one of these rare cases where nature is simpler than our models.
Yes. Well, it's not necessarily that, right? There's so many model components you can put in, but if they're all very tightly correlated, then they can cluster on a much lower dimensional hyperplane, even though the inherent dimensionality of the space is actually quite high. Think something along the lines of the fundamental plane of elliptical galaxies.
Okay, let's thank our speaker.
having me here today. For several decades, the two main tools that we had in our astronomy toolkit for X-ray observations included imaging and spectroscopy. But in 2021, with the launch of IXPE, we have for the first time the opportunity to systematically probe the polarized X-ray universe. Polarization refers to the preferential orientation of the electric and magnetic fields of the X-ray light that we're observing. And we specifically parameterize this polarization with two quantities, the polarization degree and the polarization angle, which define the percent of my total system that has this preferential orientation and also the direction of said preferred orientation. And as you can see by the equation shown here, these PD and PA values are actually composed of more fundamental quantities, these Stokes Q and U values, that I'll return to in a little bit. X-ray polarimetry can really tell us so much about accreting compact objects, but the thing that I'd like to highlight for us today is that this can really help us understand the geometry of the X-ray corona. So a long-standing question within X-ray astronomy is what shape the X-ray emitting region around these compact objects actually takes. So we can imagine that there may be a sort of vertically extended corona as shown here, a sort of shell geometry, or instead we might have something that's more horizontal and extended as a coronal geometry, a so-called slab. And the reason that polarization can actually tell us anything about this is because our polarization measurements encode the plane of scattering. So if I have an X-ray photon, let's say in this sort of horizontally extended coronal geometry shown here, we can imagine that the photon would both arise and scatter within this plane of the disk that's shown here, and my polarization will always be perpendicular to this plane of scattering. And you can extrapolate this to imagine that for vertically extended coronal geometry, I would instead have a rotation of 45 degrees of my polarization angle, or sorry, 90 degrees. And so I want to introduce us to GX13 plus 1, which is a neutron star low-mass X-ray binary and a sort of favorite target for X-ray observation. It's really bright, and it also has this persistent and really prominent outflowing feature that was first discovered through observations of blue shifting of the spectral absorption features. ITC has looked at this source a number of times, and frustratingly, we aren't actually able presently to actually constrain the geometry of the corona from sort of just preliminary analysis of the system. And so here we're looking at some simulations of the polarization degree changing with energy for both a slab and a shell geometry. And overplotted in green are IXP results. And as you can see, we can't really reject either of the models in this sort of standard interpretation. Also, sort of frustratingly encoded into this plot also is this 4 to 8 keV measurement is actually not a significant polarization detection. And this is because the measured polarization degree actually falls below my MDP. So the MDP 99 describes the minimum detectable polarization with 99% confidence. And we want to rise above this MDP 99 cutoff with our polarization degree that we measure in order to detect a polarization with sort of 3 sigma significance or greater. And as you can see, the MDP 99 scales inversely with the square root of the exposure time. So if I want to try and probe any kind of short-term variability, I'm starting to really cut into my MDP. So if I even separate my observation into 2 equal time bins, I'm already rising my MDP by a factor of 1.4. And for most of our IXP observations, we simply don't have long enough observations for us to be able to afford this rise in the MDP. And here we really run into the sort of major challenge of X-ray polarimetry, which is that while we can get away with tens to hundreds of X-ray photons in order to claim a detection or to produce an X-ray spectrum, we really need 100,000 or so photons in order for us to be able to do any kind of meaningful X-ray polarimetry. And so the question becomes, can we think of a more clever way for us to be able to actually interpret the data in order to be able to do a little bit more in terms of our study of the variability? And so here I want to return us back to the idea of the Stokes parameters. The standard method that is used in order for us to actually compute our polarization values is the sort of 2-step process. So we're going to collect our raw data from the IXP telescope. For every single photon event, we're going to calculate a Q and a U value, these Stokes parameters, and then we're going to add them all up together for all of my photon events to get my sort of observation total Q and U value. But instead, I could imagine using an unbanked maximum likelihood estimation technique, where instead of this 2-step process, I now simplify this into a single step and I construct a likelihood function which simply answers and quantifies how likely am I to get my observed sort of raw telescope data given a particular Q and U value. And there's 4 main advantages for us to actually do our analysis this way. The first is that we're able to test dependencies on additional parameters. So we'll focus on sort of variability of the polarization angle with time. And we can fold this in organically into the likelihood function with the construction of maximum likelihood estimation. We can also refine our overall Stokes parameters estimations, because if there really is short-term variability of the polarization angle within an observation, we're actually systematically underreporting the overall polarization degree, because you can imagine a varying polarization angle will, over time average, look sort of net less polarized. We'll also be able to estimate things like rotation rates without needing to actually bin our data. We can fold this time variability right into our likelihood function rather than needing to bin up the data and then look at the differences in the polarimetric properties across different time bins. And lastly, we can incorporate Bayesian methods. And so this finally allows us to move away from the sort of frequentist construction of the MVP99 and instead move towards model comparison across multiple different models describing the polarization angle behavior. And the way that this works in nested sampling is that you can define a uniform sort of unit circle prior in QU space, my Stokes space, and I can dump a bunch of live points into this prior space and calculate the likelihood shown in the color bar for this sort of schematic example here. And what I can start to do is eliminate the least likely point and move it into a shrunken prior space and continue this process iteratively until I reach some sort of convergence criteria at my maximum likelihood point. And what's extra exciting about this technique is that we can actually begin to compare our different models of what the polarization angle might be doing. So particularly, we can look at an unpolarized model. We can compare this with a constant polarization. And we can also compare this with something that assumes a linearly rotating polarization angle over the observation. And just to sort of complete the picture here, we can fold in this third dimension of the rotation rate or any other number of parameters into this likelihood calculation. And then for each of these models, in addition to the maximum likelihood value, I get a Bayesian evidence, and I can compare all of these directly with each other, despite them being sort of different levels of complexity. And so what I've done is I've taken this maximum likelihood construction, I've combined it with this nested sampling technique, and I've created a framework that I call Queen Bee for us to be able to analyze XP data. And so applying this to GX13+1, we find a number of different things. The first is that for observations where it really looks like we're not preferring any kind of rotation of the polarization angle, there's remarkable consistency with the standard technique shown in teal and the Queen Bee method shown in purple. And this color scheme will carry on for all of the rest of our plots. In observations, excitingly, where there actually is a sort of preference for rotation, we see that we are systematically raising our polarization degree. So you can see on the left, this sort of comparison of the two different techniques, assuming a constant polarization angle, but when we factor in this sort of smoothly rotating polarization angle, you see that the purple contour is at a higher polarization degree. We can also begin refining some of our non-detections. So this is one of the observations that IXP took of GX13+1. It's the light curve, and you can see there are these two dips in the light curve denoted with the sort of vertical dashed lines. And I could ask the question of, is the polarization angle variability actually coupled to entering and exiting out of those dips? And if I were to use the standard technique, there simply aren't enough photons in that small segment of data to actually be able to make a meaningful detection of polarization. But here again, because in this segment we actually see a preference for a rotation of the polarization angle, we're able to actually turn this non-detection into a 3 sigma equivalent detection of polarization, as you can see here on the plot on the right. And so now we're sort of entering into the regime of really being able to see a whole new set of physics coming from these observations, which is that instead of needing to combine all of these independent observations together in order to probe any kind of variability, we can also look at what's changing across these observations for the first time. So in particular, it's really interesting that the rotation rate that we're seeing of the polarization angle is changing quite dramatically across these observations. 42 degrees in one of the earlier observations and 174 degrees per day in a subsequent observation. And we think that this might be actually coupled to variability that we're seeing in the outflow of the system. If we return back to that very initial question about the sort of polarimetric or the corona geometry, we also see that when we apply this kind of technique, we're actually able to lift the polarization degree to a regime where we can actually say that there's a preference for this lab corona geometry in particular. And so this is a great time for me to sort of wrap up by hinting that there's limitations to this method that will really require us to actually develop new instruments, so EXTP and red SOX, which is a polar emitter that I work on also at MIT. And I'll throw up my summary here and take questions.
Any questions? Looks like everything was clear, and you're providing a tool that could help theorists model these systems. If there are no more questions, let's thank all our speakers today. Thank you.